Okay, so can you all hear me? Just put some comments in the chat, please. Just doing a quick audio test before we get going. If you can hear us, please just write a few comments so that we can check the audio, please. Yeah. Okay. All right. Cool. All right. Well, I'll just give it a few more minutes. Give some more time for people to join, and then we'll go for it. It's a little bit nippy here, isn't it? Anyone from the office joined? Can you see the list of Hello, everybody. Right, put the camera angle on me. Hello, and welcome to the first of three online webinars about the European AstroPi Challenge. And before we get going, I just want to, we've got a few housekeeping notes for you all. First, I'd like to introduce the presenters. My name's David Honess, and I'm the project manager for the AstroPi program at the Raspberry Pi Foundation. And co-presenting, we also have Laura Sack from the Raspberry Pi education team.
Hello, everyone.
And if you want to use the chat feature, you should be looking at a window that has a live chat feature sort of over there somewhere. And you need to have a Google sign-in for that. So if you haven't got a Google login account and you want to use the chat, you will have to go off and create yourself a quick Google login. And I don't think that takes very long. That will be moderated by Raspberry Pi staff and by Laura. So if you have any questions, you can actually ask them in that. And if there are particularly pertinent questions, Laura will interrupt me and I'll answer them as we're going along. The other thing to note is ideally, you ought to be on a nice speed internet connection when you're watching something like this. It will be broadcast in HD, but if you, say, for example, in a coffee shop and you're on a kind of the public Wi-Fi in a coffee shop or something like that, and that's not very high speed, then the likelihood is that you might see some sort of blurring and some pixelation whilst you're watching this. So please try and make sure you're on a good internet connection whilst you're watching this webinar. The other thing also is that during the webinar, we're going to be showing you images of the Sense hat, which is one of the peripherals that you've got in your AstroPi kits. And these the Sense hat is has a matrix of RGB LEDs which are pulsed at about 60 hertz, and this is notoriously difficult to film. If anyone gets their mobile phone out and tries to like video the Sense hat whilst it's recording, you'll see this kind of like pulsing effect, which is very similar to you know, when you used to point a TV camera at a TV and you see the kind of like blurring lines. But we've tried to set up the lighting in here so that it looks okay. So later on in the webinar, when it comes to that point, you'll see that I'll hold one up, and you should be able to read the text, and it should be okay. But if you're struggling to read what comes up on it, or you can't see it, just put a comment in the live chat. Okay. And lastly, after this webinar is over, it's going to be about 2 hours long. So it's a long old session. The replay of this webinar will be available on this same URL as you're actually on at the moment. So you can bookmark the URL and come back to it later if you want to. Okay. All right. So the first thing we're going to do, let's switch to the overhead camera just a second. What we're going to do firstly is just you should have all received one of these kits in the post. Okay. Now, I know that there's some issues with some shipping, so if you haven't received your kit yet, you'll need to take that up with ESA. So I'll send an email to teachers@esa.in to inform them that you haven't got your kit yet. Okay. So first thing I want to do before we do anything, I just want to establish that when you've received your kit, the contents of it is correct, and you've not got anything missing from the kit. So let's just go ahead and open it. And what I'm going to do, I'm just going to show you all the content. Let's go ahead and open it. So first thing you'll have is a HDMI lead. Okay. You'll have a Raspberry Pi 3. Okay, Raspberry Pi 3. You'll have the Sense app, all in separate bags. Okay. And then you'll have both cameras. So you've got camera and noir camera. Now, they're basically the same, but this camera here has had its infrared exclusion filter removed. What that means is that you can actually see the infrared spectrum of light with this camera. But that's not the thermal spectrum of infrared, it's just the near infrared spectrum. So you can do certain scientific things with that, whereas this camera is just the visible spectrum, just exactly like what you've got in your mobile phone. Okay. And then you've got also a HDMI to VGA adapter. I'll open this bag. Okay. So there you go. Little Pi Hut logo on it. Okay. And obviously what you would do is if you haven't got a modern monitor that can do HDMI, which is that kind of connector, you can convert it to using VGA, which is that old style of video connector. Depending on the kind of monitors that you've got available in your school, you might not need to use this, you might need to use it. Okay, and we'll come on to that in a second. You've also got a power supply, a Raspberry Pi official power supply. And then you've got this bag. Okay, and this bag has got lots of little bits and pieces in it. Now that is for building the Astro Pi flight unit. So you can see I've got one here. That's actually a genuine Astro Pi flight unit there. Okay. Now, when you go off and build one of these, you won't be able to make it out of aluminium like this. What the idea is that you'll use a 3D printer and you'll end up with something that looks a bit more like this. Okay, that's just printed in black ABS. Okay, and we'll come on to that later. Okay, so that's what that bag is for. Okay, and there's a video on the ESA YouTube channel which you can go and watch, which explains how to make it. And you should also have, this is very important, the SD card. The bootable SD card. Okay, that comes in a little bag like that. Okay, so if there's any of that missing, then you need to email ESA and tell them. Okay, so put that box out of the way for now. Okay, so the next thing you need to do is there are a number of things that you're going to need to provide yourself. Okay, to actually use all this equipment. Okay, so let's just go through that. What else you need? You'll need a USB keyboard, a USB mouse. You'll need a small screwdriver. Okay, doesn't have to be huge. It's just it's a cross-head screwdriver. Okay, and then you'll need either, depending on the kind of monitor you've got, a HDMI cable, which has got that kind of connector on it, or a VGA cable, which has got that kind of connector on it. Okay, and that obviously depends on the kind of monitor you've got. And then also you will need an actual monitor. Okay, so basically those are the things you'll need to provide when you're using the kit. Okay, and hopefully those are all things that I would expect most schools to just have lying around. Okay, so let's do the out of the box setup then. So that's the next stage. We're just going to go straight on to the out of the box setup. What do we do first? Okay, so firstly, let's just look at the Raspberry Pi 3. Take that out. So open this box, and inside it you will find there's a little anti-static bag, and you just open that, and inside there's this little green circuit board. Now that is the Raspberry Pi computer. Okay, and that is actually a full computer. Okay, so if you've never seen one of these before, think of an empty PC case with one of these inside it. Okay, it's not a USB peripheral that you plug into your computer to make it work. It is a computer in its own right. And if you let's just go around the edge of it, what you've got here is the HDMI video output port. Okay, you've got an Ethernet port. You've got 4 USB ports to plug your keyboard and mouse in. Okay, this header here is used for input and output, called general purpose I/O. You've got a camera connector there, and also a display connector up there, which is actually only if you use one of our display peripherals. And then the power goes into that little micro USB socket at the end there. So it is a completely standalone computer. Okay, so what you're going to do, the first thing it needs is the SD card. So where did I put that? Let's hope I haven't lost anything yet.
Is it in the box?
Oh, did I put it in the box? Yeah, I might have left it in the box. Oh, yeah, left it in the box. Whoops. There you go. So the SD card is like the hard drive. Okay, so just open that, pop that out. And then what you've got is a full SD adapter, but with a micro SD card slot in it. Now, if you look on the bottom of your Raspberry Pi, you'll see there's this silver thing here. Okay, that's the actual card slot for it. And you can obviously see that that's way too big for it. But if you look closely, you see down at this bottom, there's a little tab there. And if you do that, that comes out. Okay, so this is only for if you wanted to put this into a PC or some other computer to access it. But so essentially what you do, just take this out, pop it in here like this. Okay, and that's basically the boot drive that it's going to boot from. Okay, so I'm going to use it with HDMI because this is a HDMI monitor. But essentially, if you were going to use the VGA adapter, all you would do is pop that in there like that, and then you'd get your VGA cable. Sorry for the noise. And then you just plug it straight in there like that. Okay, and that can go off to your VGA monitor on the other end of that. Okay, and that should just work. Now, if it doesn't just work, there'll be the main cause of that kind of problem. If you plug in your Raspberry Pi and turn it on, you don't see anything when you're using one of these things. It's because this thing is actually quite simplistic, and all it does is it just converts the signal coming from the HDMI digital signal coming from the Raspberry Pi to an analog signal of the same resolution. Okay. Now, by default, the Raspberry Pi wants to output video in HD, which is 1920 by 1080. So unless your monitor can support that, you might find that you just don't see anything. And what you can do is you can actually edit a file on the Raspberry Pi to force it into a lower resolution video mode. Now, if you need to find out how to do that, you can just Google that. That's actually like quite a common operation that people do. And you edit a file called config.txt, which is a little bit like the BIOS of the Raspberry Pi, and you just add some lines into that, which will force it into another video mode, like a lower resolution. You know, you can go down as low as 640 by 480 if you want to, using this. Okay, but just for now, I'm just going to use HDMI because that's easier. Okay, so first off, plug in the HDMI to that one, and then that's going to go around the back of my monitor. Sorry if there's a bit of camera shake. Okay, so my monitor's plugged in, and then I'm going to plug in my USB mouse and my USB keyboard. Okay, I'm not going to install the Sense app just yet, just in case you were all wondering about that. I'm actually not going to do that until just in a little bit. I'm not going to use the camera module yet either. Okay. So now that's pretty much everything. I'm pretty much plugged in. I'm ready to turn this on. Okay. Now, when I turn this on, I actually can't screencast it because the noob software that's going to run now to install it won't actually allow me to run like a desktop capture mode on it. So what I'm actually going to have to do, really sorry, but I'm going to have to hold the monitor underneath this camera so you can see it. So when you plug it in, turn your monitor on, and then what you should see is something like this. There you go. So you've got a Raspberry Pi, and what you'll see now is lots of different aerospace logos cycling. Okay, so we just wait for a second. You'll see that number starts increasing, and then you'll start seeing different pictures come up. So there's the Astro Pi logo. This is what you'll see when you first turn it on. You won't see this every time. This is just like installing the operating system, like when you get a brand new PC. And we're not going to sit here and watch all of this, but I'm just showing you that when you're installing it, this is the kind of thing you should see. And then we will go into like a nice desktop interface, which you'll see in a second. Okay. So I'm going to just unplug that now. Now what I'm actually going to do is run this through a VNC session where I'm going to screencast a VNC session. So let's just get that out of the way. Okay. So before I go into the next stage, has anybody got any questions? You can go back to the main camera screen now. Has anybody got any questions about that setup process in the chat?
We haven't got any questions about the setup, I don't think, at the moment.
Excellent. Okay. Right. We can just move straight on then. Right. So you can't quite see this yet, but I'm actually just going to boot this up with the Ethernet input installed, so I can just use this laptop that I've got here to screencast it.
I do have one question from Anna Moxes saying about reinstalling the operating system that came preloaded on the card. Which version should they use?
Well, if you want to reinstall it, there is the way Noobs works is that you have you can actually reboot and hold down Shift, and that then takes you back into a little menu which lets you completely wipe it back to a clean OS, which is kind of useful if the kids do anything really stupid and just mess it up so it doesn't boot anymore. You can do that and just completely clean it back to a clean OS. But if you want to go back to standard Raspbian, so what you've got on those SD cards is a normal Raspbian OS, which is basically the most up-to-date version. So you can just go to raspberrypi.org/downloads and just download latest Raspbian with Pixel, and that will be essentially what you've got. But you've got a couple of extra mods with the OSs that shipped with the ESA kits, such as the desktop logo and a few other little settings which make things easier for you later on. Okay. Right, so now what I'm going to do, just quickly set up my screencast. Right, almost there. Any other questions that came up?
No, lots of people saying hello.
Okay.
Welcome, everybody.
Right, okay, so can you just switch to that other desktop view? So can you all see that desktop? That's the actual, what you should be seeing when you boot up the, when the Noob's installation is finished and you boot into Raspbian, this is basically the desktop that you see. You should have an ESA background if you've got one of the ESA branded Astro Pi kits. Otherwise, you will see kind of like a road going off into the distance if you're on standard Raspbian. Okay. So first thing I just want to quickly show you is connecting to Wi-Fi. How do you connect it to the Wi-Fi? Now the Raspberry Pi has got. Let me just switch back to the main view. Just a sec. I'm just going to hold up the Raspberry Pi to the camera here. Just over here, where I'm pointing with the SD card, is actually a little Wi-Fi aerial just there, that little white chip, just underneath where it says "Made in the UK." So if you look at it closely, there's a little kind of white cuboid just above where it says "Made in the UK," and that's the Wi-Fi aerial, which you can show the kids. And basically, what you do is you go up to on the screencast now. If you go up to this screen here, I'm actually on Ethernet at the moment, so I can. This will probably be turned on by default, but you can go turn on Wi-Fi, and then you can see that there are all of these like networks that are available. I've logged into CTV there, which is Cambridge TV, which is where we are. And essentially, that's all you do. You just click on one. For example, like if I go to this guest one, it's going to now prompt me for the password. Or at least it should do. Oh no! It's obviously the same. Let's go BT Wi-Fi. No. Okay, well, what should happen is the moment you come in here and click on any of these, it should actually just, there you go, like that. And then you just type in the Wi-Fi password into there and click OK. And that's you on the Wi-Fi, okay? But if you plug it into Ethernet, you'll just see these two arrows like that. Okay, and you can sort of hover over there and you can see what the IP address is. All right. Okay, so before we go any further, I just want to do a quick side note about there are two emulators for the actual Astro Pi SenseHat hardware. So let's just quickly go through them. There's one which is actually built into the OS that you're using. So if you go to Programming and then SenseHat Emulator down here, click that. And this window comes up and you can resize it if you want to, make it a bit bigger. And essentially what this is doing, this is emulating the SenseHat hardware. Okay, and you can move these sliders to change the sensor values, and that's quite a nice thing to use if you want to send them home with homework or anything like that. And there's some, you can open examples like that. You can go simple, humidity, intermediate, and you can just load these and run them. Okay. Also, there's one available in the web browser, and this is probably slightly better if you want to give the kids homework to do. Just wait for my browser to come up. Okay, so you go to trinket.io/sense-hat. Okay, and then just wait for it to load a second. Excuse me. It's just taking a while to load. Okay, so what you have is a code window, built-in code window on the left, and then you have like a virtual SenseHat on the right, and you can again move these sliders around to make it do stuff. Okay, and that's basically a really nice. You can rotate the SenseHat as well if you want to. So yeah, if you want to give the kids homework, that's quite a nice little thing to use as well. So go and explore that. Okay.
We had a little question, Dave, on the chat about what should we do if the time is not correct on the Raspberry Pi.
Okay. There is. I think you can use if you go to the command prompt, you can go sudo raspi-config, and there's a I think it's in here, isn't it? Internationalization options. Yeah, change locale and then change time zone. You can use, usually if you're, most people, you might find that your clock is 1 hour out if you're in Europe, and that may be because you're still in, the Raspberry Pi still thinks it's in UTC. Okay, so that's the command you go and just change your time zone in there. Okay. Right. So what I'm now going to do is install the SenseHat. That's going to be the next stage. We've booted up. You've done your Noobs installation. We're now going to go and install the SenseHat. So I'm actually going to stop sharing this. You put me back to the main camera. and I'm going to go sudo on there. Okay, so let's now go back to the overhead view, and we're going to install the sense app. Okay, so take your sense app box, just open it. Get a little bit of information in there, and you also will have this little mounting kit. Sense app's in this bag, and you have this little bag of screws, which is designed to just mount only the sense app to the Raspberry Pi. We're not going to go straight into making the Astro Pi flight unit because that's quite a long old process. And if you just want to get going quickly in the classroom, this is what you want to do. Okay, so there you go. There's the sense app. So let's just quickly mount it to the Raspberry Pi. You can get away without using these screws if you want to. And essentially what happens is that those two connectors fit together, and then the 4 mounting holes in the corner, you put these standoffs in, and that holds it nice and rigid. Okay, and that'll stop the kids from being able to cantilever it and possibly make it touch so you get any short circuits or anything. So what I would do is take a screw and just pop it through one of the holes of the Raspberry Pi first. Okay, and then we're going to just take one of those black standoffs and just screw it on like that with your fingers. It doesn't have to be too hugely tight. So that's what you basically want to have. Just do that. You should have 8 screws and 4 of the standoffs. Don't need the screwdriver until the very end. Okay. Now, apologise if the overhead camera loses focus. We had a bit of a job trying to get the lighting right so that the autofocus on that camera didn't go mad. Because we are just using webcams for this. We're not using the really expensive studio cameras that are in here. But we might do one day. So almost there. Okay. Right, now you've got the 4 standoffs on. Okay, take the sense app, line it up with the GPIO header. Okay, make sure that you're not like one port to the left or right, and then you're just gonna pop it together and just push, and that's it. It just locks down like that. And now you take the other screws and just screw them into the top. Okay, and this is where you can use the screwdriver. Just pop that in there. Just quickly do that up. Now, when you get to the end of it, if you as you tighten it, it'll tighten both screws at the same time. You probably see the sense hat itself move a little bit, the actual standoff itself turn a little bit when you do this. Okay. You can, if you are being really quick, you can just do the 2 that are on this side, on the HDMI side, because that side there is held rigid by that that connector anyway. So you could just do 2 of the standoffs if you're in a hurry. Okay. Last one. Okay, so there you go. That's basically what you want to do. That's like stage 1 of preparing for Astro Pi. So you can, all the kits that you get, you can just do this for, and then you're ready to go. Okay. Now, if you write code that's on one of these, it can run straight away on an actual flight unit. Okay. So you can see that if you look at you can look at the equivalency of this. That's basically what's in there like that, and you can see like that's how it lines up. All right. So now we're going to turn it back on. Now, when you do this, you should see the following. Now, if we switch back to the main view, Obviously, there's no power switch on a Raspberry Pi, so when you turn it on, you are literally just hot plugging it. So you should see a rainbow pattern, which you might not be able to see here, which should then disappear after about, I don't know, about 10-15 seconds. It should just go blank. Okay. There you go. Okay, so that's the normal behavior. If the rainbow pattern remains forever, then the Raspberry Pi isn't detecting the sensor. So the normal procedure is for it to boot up, and then it clears the screen once it's detected the Raspberry Pi and installed the drivers for it. Okay. Right, now I'm just going to quickly set up my screencast again.
Just while you're setting up, David, you've got time for a question?
Yep, go for it.
So somebody has asked for the instructions that they have to timestamp data, going back to the time zone question from before, and they asked what format and time zone do you prefer?
We prefer GMT because that's the time zone that the ISS runs on, and also will be the when your code runs on the ISS, the Astro Pi's flight units that are up there are time synchronized to GMT. Okay.
Brilliant, thank you. And there's just another question, also going back to a previous question, which is if you somehow manage to corrupt or lose the data from your SD card, is it possible to reinstall the special Astro Pi operating system? Yes,
only if your SD, if it still works, if you boot up and you see the noobs menu, you can hold down Shift as you're booting, and then you should get to this menu where you can reinstall the ESA Raspbian. Which should come up, and you just click install on that, and that will completely reinstall it. If not, if your SD card is just completely non-bootable, you just turn it, you just plug it in, and all you see is the red light. Then you'll need to go off and download. The best thing to do is go off and download a fresh Raspbian again. Okay. So right, so we can switch now to the desktop. And what you should find now is actually no, we won't do that yet. Let's go back to the view of me. What I'm going to do now is just do a quick walkthrough around the sensor. So let's just quickly just go as close to the camera as we can with this. So what you've got this 8 matrix of LEDs, and these are RGB LEDs. Okay, so they can do any colors that you want to make, and we'll go through how to use them in a minute. And this is a really nice little thing to do with the kids, if you know what I mean, so they can actually see what all the components are on here and what they do. So for example, this thing here is a joystick, and you can actually move this up and down, left and right, and that's actually mapped to your cursor keys and enter on your keyboard. So when you press these, the computer thinks it's a keyboard that's actually being pressed. And then what you've also got is right next to the USB ports, if you look really closely, you probably won't be able to see this on this camera, but you've got those two little black squares just where my finger is. That's the humidity and the pressure sensor, and if you look really closely at the sensor, you can see the words pressure and humidity on it. Okay, and then just this one here, that's the movement sensor, and if you read this little line here, it says Excel Gyro Mag, and that's 3 sensors in one. Okay, and then that's a little Atmel up there which drives these LEDs, and there's a little LED driver chip down there as well. Okay, right, so now let's go to the desktop again, and what I'm going to do, we're going to use the Python language, which is the main language that we use on the Raspberry Pi for education purposes. And just a quick note about Python, if there's anybody out there that's actually I'm just going to quickly turn off my Wi-Fi. If anyone's never used Python before, there's some nice free learning resources online that you can go and look at. And one of the ones that I quite like is this one here, the Code Academy one, which you can get to if you go to codeacademy.com/learn/Python. And if you just go through this, there's 8 projects that you do, and by the time you finish those, you'll be quite comfortable with Python. And this is really only necessary if you've never done any Python before. Okay, so I just wanted to sort of point out that that's available. Go to that URL, and you can work through these projects and just get the kids comfortable with using Python as a language before we you really dive into all this. Okay. So on the Raspberry Pi, the way we use Python is to use a tool called idle. So if you go to the start menu at the top, programming, and then we're going to go down where it says Python 3 idle. Okay, not Python 2, we're going to use Python 3. Click on that. And then this window comes up. Now I've made the font big. You probably won't have a large font on yours. I've made the font big here deliberately so that you can all read it, especially if you're having bandwidth issues or anything like that. So we're going to quickly write a little program. This is a really good thing to do with your kids, to get them to the point where they're actually getting a nice payoff out of doing this quite quickly. So let's just go File, New File, and then this blank window comes up. Now, some of you will probably have a Google logo about here, so I'm going to move this down into the right a little bit. Okay, and now what I'm going to do is just write a very simple SenseHat program. Okay, and I encourage you to do this same program with your kids, because it gets them to the point where they're seeing a nice payoff from doing this work quite quickly. So we're going to go from SenseHat, import SenseHat. Sense equals SenseHat. So that first line is basically importing the SenseHat library. Okay, and that's asking us that we want to use a pre-written library which talks to the SenseHat, and then we're creating this instance of a class called Sense. Okay, now don't worry about having to explain all that to the kids. Just get them to take it on faith that you need to type in this line. Okay, and then we're going to go sense dot show message. And then I'm going to type in hello as a string using those quotes. Hello, my name is Dave. Like that. Okay, and if you always have to make sure that when you type a string, it has to be enclosed in double or single quotes. So you can also use single quotes like this. Okay, and that is actually a 3-line program, but is actually a program that is a fully functional program. So let's just save that first. I'm going to call that hello. Okay, and then what I'm going to do is quickly switch back to me, and I'm going to run that, and you'll hopefully be able to read this. You might be seeing some reflection from the actual. That's looking a bit. Yeah, that was a little bit washed out, wasn't it? But you can see basically what happens when you do that is text comes up on the screen. Oh, I know what I need to do. Go back to the this is actually something that you guys don't need to do, but I need to do it for the low light conditions here. I need to go sense.low light equals true, because we're sitting in here in almost total darkness. So let's try that again. I'll run that again, and hopefully that's a little bit better this time. There you go. My name is Dave. And what you'll find is obviously your kids will go off and type all kinds of profanity into this and enjoy doing it immensely. But just to get them from standing start to something that's quite an enjoyable payoff for them quite quickly is to do this kind of program. Okay. So also there's lots of commands that you can type in. So when you just go back to the screencast a second, and when you basically type in sense dot, there's lots of different things that you can then type in. Okay, you can see them; they're all coming up here. All these different commands that are available to me here, and these are actually documented online. And this is a really good reference that I thoroughly encourage you to share with your students, and they will use this all the time. So I'm just going to go to this page. And it's the address for it is pythonhosted.org/sense-hat/API. And I believe that's just been pasted into the live chat. Okay, cool. All right, so you go to this page, and it essentially gives you all the commands that you can use for the SenseHat API, and it also even gives you a little code snippet that you could just copy and paste to try out and explore with. Okay, now you need to show this to your kids, okay, because they will really use this lots and lots whilst they're working on AstroPi stuff. Okay, so let's go to questions. We got any more questions?
We had a question a little while back about the temperature and humidity sensors on the Sense Hat and whether they indicate the correct values or whether they're affected by the Raspberry Pi's CPU.
Ah, right, yes. That's something we can come on to that later, but yes, there is actually a slight sort of hardware fault in the Sense Hat, which actually, if you go back to me now, so if you basically what happened is we were really rushing to try and get the Sense Hat built and tested in time for Tim Peake's launch, and what happened was there was a slight issue where we should have pulled back the top layer of the metal on the Sense Hat from those two sensors by about, I don't know, maybe a few millimeters, so that heat could not then transfer from the CPU of the Raspberry Pi underneath and thermally leak into those sensors. So what you find is the temperature sensors on both the pressure and the humidity sensor read a couple of degrees above ambient, and that's because, and it's worse on the higher end Raspberry Pis. If you've got a Pi 3, that's the warmest CPU that we've got. So you'll find that you'll see a bit of a delta from the actual ambient temperature. Now, one of the experiments that was done for Tim Peake's mission was a young lad that tried to actually write some calibration code to calibrate out that error, which is quite a fun thing to do if you're interested in maths and stuff. And you can take that really to the nth degree and look at how the CPU load of the Pi is affecting the temperature of the leak and all that kind of stuff. So you could go off and really go down that rabbit hole for your Astro Pi entry if you wanted to. But yes, there is that thermal leak issue, and sometimes what people do is they take it off and have it on a ribbon. So the actual, instead of actually having it, on top of the Raspberry Pi like that, you actually have a ribbon and then the Sense Hat on the ribbon, and that kind of then deals with that. Okay. Right. So what we're going to do now, we're going to go back to the screencast, and I'm going to minimize that. I'll keep it open just in case I need it for anything. But what we're going to do is we're going to go into looking at understanding RGB color space, okay? Because this is basically what happens with any kind of color that you want to show on the LED matrix. You need to specify in red, green, and blue color space. So let's just quickly. I've got a file on here which I'm going to show you all, which is basically just a PNG. Okay, so if you all look at these spotlights. Basically, this is a darkened room with a red, green, and blue spotlight. Okay, and they're all sort of crossing over and mixing together. And what this is known as is called additive color mixing. Okay, so you've got a green spotlight, and if it overlaps with the blue spotlight, you get cyan. And if a blue spotlight overlaps with red, you get magenta. And if red overlaps with green, you get yellow. And if they all overlap, you get white. Okay. Now, when you are explaining this to the kids, basically, what you need to tell them is that each one of these LEDs in here has got a red LED, a blue LED, and a green LED. Okay, and what you can do is by programming each of these you can actually specify how much red, how much green, and how much blue you want each LED to show. You can pretty much make any color of the rainbow. Okay, so, and a really nice way to get them into that is to just do the show message function, but in different colors. And you can do different foreground colors and different background colors. And this is just purely as an exercise to get them to understand red, green, blue color space. Okay, so let's just give that a go. I'm going to go back to the screencast, and I'm going to close that. And essentially, I'm going to keep this program that I've done here. But what I'm going to do is I'm going to define a color. I'm going to call it Col, and it's going to be, let's start off with red. So the scale for these colors is 0 to 255. Okay, and the reason for that is it's 8-bit color. Okay, now you don't need to explain too much about why that is, but it's to do with binary. Okay, so if you got 8 binary bits that are all set to 1 and you convert that to decimal, the decimal for it is 255. So you go 255, and then so that's the red element, and then you go, I'm going to go 0 blue, 0 green, and 0 blue. Okay, so that's then should give me red text. Okay, and then you come down to this point here inside the show message function, and we need to pass Col into the show message function. So you come to the end just before the bracket, put comma, and then you're going to type in text underscore color, and it's the British spelling of color, sorry about that, equals Col. All right. And then we're going to save it. Okay. Right. So if we quickly go back to me, go run module. Now, hopefully this won't look too bad. There you go. Hello. My name is Dave, but in red. Okay. Looking okay? All right. So if we go back to our picture, let's just go back to our picture. Quickly open that up again. Close that one. So what we've done is red. So let's try and do cyan. So if I just put blue in now into the code. So I'm going to go red, green, blue. So if I put that to 255, that will now give me cyan. Okay. It might not be coming out too great, but I promise you that is cyan. All right. So now let's do yellow, which is green and red. So I'm going to go 0, blue, and 255, green and red. Run that. That's probably just looking white on yours, but it is yellow. This is the reason why working with webcams can be sometimes difficult. And then what's the other one? Cyan, so green and blue.
I think the one you did earlier was magenta.
Sorry?
I think the one you did earlier was magenta.
Yeah. Okay, so I'll put 0 for that, and then 255, 0, 255. And that should, hopefully this will be visible on the camera. So this should be cyan. Oh, that's magenta again. Whoops. I'm not paying attention here. So it's cyan is blue and green only, so I need to have no red. That's what I need to do. Right. There we go. Okay. So there we go. There you go. That's got a bit of a bluish glow to it. Okay. All right. So then what you do is you just let the kids experiment with this. So, you know, just have like a 5-minute session in your lesson where you just let them go mad with mixing different colors. And obviously you've got to get them to confine themselves to between 0 and 255. Okay. So for example, if you want to do orange, it's 255 1280. Okay, that's orange. I'll just run that. Okay. Probably looks the same as red, but that is orange, isn't it? Yeah. All right. So they'll have loads of fun doing that. Okay. But then what you do is you drop the bombshell on them that they can change the background color, and then they get really excited. Okay. So let's go back to the screencast, and what I'm going to do, let's. One of my favorite colors is it's yellow. Actually, yellow and blue. So if I do that, that'll be yellow. I'm going to do back coal. Back coal equals 0, 0, 255. And then what you do so you're going to define another color, which is blue, and you've got yellow there. And then I'm going to come here at the end, just before the bracket, put another comma, and then it's back underscore color equals back coal. Okay. Now what I'm going to do is you can actually put this on multiple lines if you want to. That's what I can do. That's still perfectly fine in terms of Python. So let's save that. Now I'm going to run that. Hopefully this won't look too washed out. Oh dear, that is a bit washed out. Okay, a bit closer. Yeah, you can't really see that, but I promise you that is blue on yellow. I could try maybe turning the background colors down a little bit. Let's try turning that down to 128 on the blue and see if that works better. Is that better? You sort of still see it now. I've turned the blue on the background down a lot. But they will have loads of fun just playing with different color combinations. But what you've got to tell them, and what's really important for them to understand, is that the crew of the ISS need to see this and read it. Okay, so they've got to choose a color combination which is okay. Okay, for example, if you do light blue on dark blue, then the crew are going to be going, what? And they won't be able to see anything. Okay, so that's one of the things that you need to just drum into them when you're doing this. It's important that they understand the RGB color space. That's the point. That's the point in doing that exercise. Okay.
I've got a question on the chat just popped up. Is it possible to print text statically, obviously a bit smaller, for a set amount of time rather than having it scrolling?
Yes, you can. You can do that for single characters. Let's just. I'll quickly go back to show that. I'll go back to red. Let's just do. I'll comment out this line here. Get rid of back. Now in Python, if you want to comment out a line, it's the hash symbol like that, and you see it goes red. All right. I'm just going to comment those out. So to do a static text value, you go, and this is all in the API. If you go up here, you'll find all this up here, the documentation for it. It's sense.showLetter, and it's the same thing. You put in your text, and I'm going to go X, and then I'm going to go text underscore color equals cool, and then this should get a red X come up now. Yeah, because I've got red there. Okay. Save, and that will basically remain until I change it. There you go. Okay. And then if you wanted to sort of clear it for a, like if you wanted to do a countdown or something, you could go, import time, and then for I in range or reversed range 10 colon. This is a for loop which you will come across when you learn about Python. And then you have to convert that into a string, and then so we do that. That should, and then we need to do time.sleep 1. So that should be 1 second between each loop. So let's try that. 9. Okay, so that's a simple countdown, just using the static stuff.
That's pretty awesome.
Cool. All right. Okay, so are there any other questions about that part of it? I'll just quickly show you the API for that. If we go back to the screencast, let's just go down and find show message. Where's it gone? Yeah, there you go. That's show message. And it gives you all the things that you can send into it. You can send in scroll speed, which is quite fun to play with. You can speed up the text scroll speed. You've got the text color and the background color. You can. This is something that the kids quite enjoy. I might just go back to that and show them that. Let's comment that a lot. The kids will go mad for this bit. Put the back call. I'm actually going to take the back call out because it's really hard for them to see it then. So what you do is you come in here and you go scroll speed equals, and then you type in a number in seconds. Now, scroll speed is actually the time it takes for the message to scroll 1 column of pixels to the left. Okay, so if you set that to say 1 second, it's going to go ka-chunk, 1 second, ka-chunk, 1 second, ka-chunk, and it's going to be like you'll be waiting for ages to see what the message is. So you have to type in a fraction of a second here, and I usually suggest to start around 0.0. The default I think is 0.07. So try 0.05, and then that should then scroll it a bit faster. Let's just go back to that run. Okay. And again, also remember when you're showing them this, that the readability for it on the space station is going to be important. So get them to keep that in their mind when they're designing and using this kind of this feature. Okay.
We also had a question about, is it possible to show text over an 8x8 image?
With our current API, no. You can only set the background color. What you could do is rewrite this. You would have to rewrite the actual the show message function to do that. So I'm afraid not currently with our API, but we could add that as a feature in the future.
We've had lots of questions about sensors, but I'm guessing you might come.
We're going to come on to the sensors. Yeah, we will. Yeah. Okay. All right. Okay. All right. Okay. Cool. So, are there any other questions specifically about the show messaging and the LEDs and the colors and stuff?
Not that we've got at the moment.
All right.
Keep them coming though.
Okay. All right. Okay. So what I'm going to do is I'm going to start a new file. Okay, so the next thing we're going to do is we're going to just draw some shapes and icons with the Sense hat. Now, this is obviously quite a nice thing to do. Is when your program's running on a space station, you want to maybe show some status symbols when you're loading, or when you're performing a particular calculation that takes a while or something. You might want to show something on the LED matrix which shows the crew that it's working. And usually having something that's changing every now and then is a good thing, because otherwise they'll look at it and they might think, oh, it's stopped, what's going on, sort of thing. So my advice is when you're writing your code, have something always moving or changing on the screen all the time. So what we're going to do, there is a function called set pixels, which allows you to draw an entire screen at once of pixels. Okay, so what we're going to do is I'm just going to show you how to do that. And the first thing you do, go back to the screencast. We're going to I'm going to save this one as pixels or pix. Save it. First thing you need to do is define a list. Okay, called pixels. It doesn't have to be called pixels, it can be called anything. And the list denoter in Python is these angle brackets. And then you put stuff inside there. Okay. Now what I like to do is, let's just do black and white. So I'm going to do say B for blank, and then I'm going to go 0, 0, 0, and that's a color, that's blank. And then I'm going to do white, which is 255, 255, 255. Okay, now you'll see what's going to happen here. We're going to go inside this pixels array, and I'm going to create multiple copies of this B and W. Okay, and you'll see what's going on as I do this. So B, 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 B. That's one row of LEDs. Okay, and then we need 8 rows like that. So copy and paste is your friend here. Copy, paste. Okay, and just keep going like that until you've got 8 rows. Now that's it now, and then you take away that last comma. Okay, you don't need that last comma. Okay, so you get rid of that. Okay, so I'm just going to maximize this a bit. Now what we're going to do is we need to actually draw what we need to call sense.setPixels, and then you pass in pixels like that, or whatever you've called this. I could call this Dave, for example, and then pass in Dave down there. Right, now at the moment I've just got that fully filled up with blank. Okay, so at the moment if I run this, I'm not going to see anything on my LED matrix because it's just blank. But what I'm going to do, I'm going to go here, and you can see now I'm starting to draw in it. I can go W, W, and I'm actually going to draw a horizontal line going from top left to bottom right, like that. Okay, so now I'm going to run that. You should see that we get a nice little horizontal line. There we go. Okay, and you can do anything you want with this. You could actually like it, and you can add as many colors. I find that it's easier to use single character names for the colors, because then when you're working in that kind of space like that, it's easier for you to actually to follow what's going on and to almost see the picture in the thing. So I'm going to put an R in here as well, and maybe put a red line going the other direction. So I'm going to go like this and go R, R. So I've got a white line and a red line. Okay. Okay. And you can see also, if you go to the API reference, there's some stuff about set pixels up here. Where's that gone? There you go, set pixels, and you can see there's an example here with a question mark. So I can just copy and paste that if you want. Copy into my code. And I'll just replace that line there with it. Oh, and then I need to use let's make that X and that one O, so that it's compatible with the lines I put in there. And then I can put question mark into set pixels. Right, so if I run that, it's a white background with a red question mark. So let's just set that to 0, 0, 0, and then you'll be able to see it. Damn these webcams, eh? Right, okay, let's try that one. There you go, that's a bit better. Okay, so you can basically make any kind of shape that you can with 8x8 pixels. So any kind of icons or iconography is a really good thing to use here, because you can't really show very high res or detailed pictures with 8x8. So you get the kids thinking about that kind of thing. Okay, there is a load image function also in the API, which you can do if you've got some kind of you know, like Adobe Illustrator, or you know, you can use load image of a PNG file, as long as it's an 8x8 image. Has to be an 8x8 image. Okay, so there's there's Space Invader.png there. I can probably load that actually. Let's just I think I have got that example here actually. Go open. Where is it? Sense app examples. Space Invader. Okay, so I probably need to go home slash. I'm just putting the path into the file. You have to do this if you've right, if I just run that now, that should work okay. If you're running it in the same directory, you don't need to put the full path in, but hopefully now I get a little Space Invader come up. There you go. Okay, and that's actually loaded from a file on disk. If I just go and find that file, let's just go and have a look at it. Examples. You see there it is there. That's actually an 8x8 PNG. So you can, if there's lots of icons that you want to use, sometimes it's better if you just store them as PNG files, as opposed to doing it this sort of manual way. Okay, but it's up to you, whichever way you want to go with it. Okay.
I have a question. Is it possible to darken the brightness of the matrix even further?
Yes. So what you would do then is, if you want to make it even further, so you just reduce this number here. So let's go back to my question mark now, and at 255 is the maximum. So if I say put that to 128, that's half the brightness as it was. So the number actually is the intensity of the color. Okay. So let's just try that again, and hopefully you should see that that's now a bit darker. If I go even further, if I go down to say 64, probably barely be able to see it. Okay. So that's basically how you do that. Okay, so now the next section I'm going to go on to is show you how to do like simple animations with something called set pixel, which is a single element. Okay, so what I'm going to do is I'm going to let's just copy those lines again. I'm going to do a brand new program. I'm going to close that one down. Close that as well. Okay, and we're going to save this as pixel. So say for example you wanted to show some kind of animation happening, and you wanted actually individual pixels to be changing separately, as opposed to just doing a huge dump. You can do animations if you call set pixels multiple times and you've got lots of frames. You can do that, but sometimes it's nice to show sort of like a little row of pixels just going duh, 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 and that's quite nice as well. So let's do, I'll do a col, which is going to be red. Which col equals 25500, and then I'm going to do a for loop. Okay, so I'm going to go for x in range 8 sense dot set underscore pixel, and then I'm going to do x, and I'm going to do 0. I'm just going to hard code y 0, and then I'm going to put col as my color. And then I've got import time up there. Let's go time.sleep 0.5. So what that should do on the matrix, we'll just go back to this a minute. It's actually got a coordinate system. So you've got the X across and Y down. Okay. Now 0, 0 is up here. Okay. And then 7, 7 is down there. Okay. So actually the 0 is the top corner. It's not the bottom corner. It's up here. Okay. So you should see that this will give us a row of pixels slowly appearing along the top. Okay. I'm just going to add one extra command into this, which is sense.clear. And what that does is that blanks the LED matrix completely. Okay, let's just do that. So hopefully this works. I haven't got any syntax errors. There you go. All right. So you can see that. I'll just do that again for if anyone missed it. So you could do that whilst you're waiting for something to load or something if you wanted to. Now what I could also do is a nested for loop now. I could do something like for y in range 8, colon. And then now with Python, indentation is how you don't have like begin and end tags in Python, you just have indentation. So the easiest way to make sure your indentation is right is to delete your line and press enter again, and then it automatically puts it in for you. So now I've got for x in range 8, and inside that I've got for y in range 8. So if I get x now and y, this will, I might increase the speed a bit to say 0.2. And what you should see is this will slowly fill up the entire SenseMap screen. Okay. We're going in that direction. Now, if you want to go in the other direction, you just swap around the X and Y. So if I go back to the screen, if I want to go the other way, I'll just do the Y first and then iterate the X second. Okay. So that will then give us the other orientation. All right. So that's the kind of thing you can do. You could actually have like a little pixel that's moving around based on the joystick or something if you wanted to, or based on the accelerometer or whatever you want. Okay. So are there any questions on using set pixel?
We haven't got a question on set pixel, but going back to your Space Invader, there's a question of whether you can use animated GIFs to display. No.
So that would be quite a nice idea, actually. If you could do animated GIFs of 8x8, that's a really good feature request, actually. So if you want to add that as an issue, go to GitHub, and I'll just go to it here. I'll just open a new tab. Go to github.com/rpy-distro/python-sense-hat. And this is where the actual code lives. You go into issues and add an issue there. Okay. And so these are currently the open ones at the moment. You just go new issue and type it in and just add it as a feature request. All right.
Sorry, what was that address again?
Oh, it was, hopefully it's kept it.
Is it github.com/rpy-distro/python-sense-hat?
Yeah, I'll just type it in again. There you go. It's actually on the screencast now. All right. So github.com rp capital I lowercase dash distro. Okay. We'll put that in the SenseMap. If you've got any other feature requests, pop them in there as requests. Okay. And then the next time we do a round of development on it, we'll consider doing them. Okay. Right. So. Okay. So have we got any more questions on that?
Not at the moment.
Okay, cool. So now we're on to the environmental sensors. Woohoo. Okay.
Lots of people are looking forward to those.
Okay, right. Okay. So one of the most fun things that I've done when I've done these workshops before is getting the kids to program a simple loop which just displays the humidity on the screen, not on LED matrix yet, just on their main screen. And then you exhale onto the humidity sensor and they see it going up and down. And that is a really profound thing for a lot of kids. They're actually seeing that the computer is reacting to something in the physical world, and they're doing something that's outside of the screen. Okay, so let's just try that quickly. I'm going to close that, and we're going to go File, New File on your Python shell. And have I got that in there still? Yeah, okay, cool. And I'm going to move that out of the way of the Google logo. And I'm going to save this one as hum for humidity. Right, so all you do, just do a while true. And this is kind of like the forever block in Scratch, just like an endless loop, which you can break out of using Control-C. And then we're going to go print sense.humidity, like that. Okay. And humidity is always a really good one to start off with, because it's you know, really nice, like a very interactive thing. And what we're going to do is just hit run on that, and what you'll see is it will just fill the screen with numbers. Okay, so it's about 40% humidity in this studio that we're in. Okay, now if you go back to the main screen, I'm just going to exhale on this. When I exhale, switch back to the screencast. Okay. Okay, so I've got it above 100. That's a slight bug with the firmware. Okay, you see it's going back down quite quickly as I sort of waft it, but you can see it's reacting, the firmware reacting, sorry, to my breath. Come back up again. And what you'll find is the kids they'll go mad for this, because it's so sensitive. And just a word of safety, you will always get one kid who will hyperventilate. Okay, they'll be sitting there going, okay, so you just got to make sure that nobody does that. Okay, just prep them to make sure to not get overexcited and do that, because you don't want to have to drive anyone to A&E. Okay, so once you've done that, this is probably one of the best ways to detect crew presence as well. So if the crew are actually working anywhere near the AstroPi flight unit, the flight unit does have a hole on it right above where that sensor is, that little hole on the front. That's not for the camera's on the bottom. Okay, that hole there is right above the humidity sensor, so it has a fairly good chance of detecting when they're nearby. Okay, and all you need to do is detect an increase in humidity of about, maybe, I don't know, 4%, because that would probably be an increase of about 4%. It's probably enough to make you think that a crew member is nearby. Okay, because the environmental controls and systems on the ISS are constantly scrubbing the air and keeping the air at constant humidity. So what you'll be detecting is localized increases in the humidity. Now, if you wanted to do some kind of interactive thing with the LED matrix with this, there's a nice little example I can show you here, which I can just open, which I've pre-made. Here we go. I'm going to change that to hat. This is one of the ones that comes with the emulator. So essentially what we're doing, don't need that up there. I'm going to move the window again for everybody. You've got the sense hat being imported, creating the sense hat, and then we've got green and white. Okay, so while true, we're reading the humidity, sense.humidity. So what we're doing, actually, by doing that, we're copying it into a local variable, so that we can process that instance of that measurement for the rest of the loop. Because every time you access sense.humidity, the humidity value could have changed. So it's a good idea, so that your maths is right, is that you keep a copy of it and then process that copy. So then you've got humidity value equals 64 times humidity divided by 100. What that's doing is that's a scale conversion. Okay, so the scale of humidity is 0 to 100. But the scale on the LED matrix, if you want to use the entire array of LEDs on there, that's 0 to 64. So you do a little scale conversion like that. And then this here is actually it's kind of a bit of advanced Python, but basically that is what we call an array constructor, where you've gone pixels equals open bracket and then green if I greater than less than humidity value, else white for I in range 64. So that line just builds a big array of either of those colors based on the level of the humidity. So what you should get is a green and white bar that moves up and down with humidity. Okay, So if you wanted to get that, just go to your SenseApp emulator, and then you go open example, and then you find it in, I think it's under basic. Okay, so let's just run that, and what you should see. Now that's probably impossible to see, so let's just change that so that we're using a different color. So let's use, instead of white, let's use blank. That's probably going to be a bit better for everybody. Okay, so there you go. Now you see that one of those little pixels is flickering, and that's what we call jitter. And that's something that you should see when you're representing the sensor on here. Now if I just exhale onto this, you see it's going up. It should go back down naturally. All right. There you go. And that's quite fun. There's lots of different ways you could represent that on the LED matrix. You could have bars that go up. You could have something like this, which fills up the LED matrix like a wave. Anything you want to do, really. Okay. So, are there any questions about the humidity sensor?
We've got a couple, yes.
Okay.
So, question about sort of writing some code for where astronauts are present. Is it possible to get a baseline reading without an astronaut present in the capsule? Yeah,
I mean, that's a good thing you should do. I mean, when your code starts, what I would do is maybe spend the first, I don't know, 60 seconds of your code just measuring a baseline. And what's good when you're measuring the baseline, keep reading the temperature. Sorry, keep reading the humidity until you don't see any variance in it. So what you should do is, so for example, keep adding them into a list. And then every, say, 100th measurement, you average that list. And if the variance in that list is quite high, then you know that you should keep on trying to get a baseline. And if you go around again and just get another 100 measurements, and if the variance is then like maybe half a degree, then you know that, okay, it's probably stable. That can be my baseline. And then once you've got your baseline, obviously in your main loop, you're going to be looking for an increase from that baseline. But what's important is you have a timeout and remeasure your baseline, say, every 15 minutes, because otherwise you start to ratchet up, if you see what I mean. So, for example, you might only ever, if the humidity is decreasing on the decrease, what you definitely need to do is make sure that your baseline also gets remeasured so that your baseline goes down as well. Okay, otherwise you get this ratchet effect where you can only go up with your baseline. Okay, so just be aware of that. If you want to have a look at some code that's actually that did this, go back to the screencast. I'm just going to go to the AstroPi website, which is here, astro-pi.org. You can get access to all the previous code that has one AstroPi on here. So if you go to Principia, and then you go to, say, 2015 winners, and then look at this one, crew detector, and you can look at this. These guys basically did that. And what I don't want to see is everybody ripping off this code, but this shows the technique. If you go to this one here, sweaty astronaut. Okay, so have a look at what they did here. Have a look at these functions. Okay.
We had another question, which is, do you have any idea of what humidity value the ISS operates at?
Yes. Okay, so it's a good thing to do is if you want to characterize. I'm going to go to the AstroPi website again. There's actually some data logging that was done during the peak mission, which you can access and look at, and that gives you some really good characterizations of what all the sensors should be reading. So if you go to this learning resources page at the top, come down, and you should find that there's one called flight data analysis. Click on that, and then we go down, click get started. And then on this page, there's some links. I mean, you don't have to read all this. You can go down and find these links to. These are the column headers of the CSV files that you can download. Show you what each one means. And then there are these files here that you can click and download. And these were actually actual sensor measurements as recorded by the payload. This one here is especially good because it's a 4-week-long session where you've got measurements every 10 seconds for 4 whole weeks. So it's a really good resource if you want to go there, download that, look at those measurements, and then you can see about where the humidity should be on the ISS. Right.
I think that also helps to answer another question, which was how often is it reliable to measure the humidity? If it was every 10 seconds, would that be a sensible?
You could measure it as fast as you can, actually, if you want to. Like, for example, on that code, on this, for example, here, there's no time delay in there, so that's going to basically just do it as fast as you can. And it's pretty okay to just to absolutely, you know, to rag the CPU whilst measuring it if you want to. I mean, it's not going to harm the Astro Pi or anything. Okay. All right. So where are we? Okay. So there is also the pressure sensor. Now I'm just going to do that now. I'm going to put pressure as well. All I'm going to do is just go to this program. Again, I'm going to just change that to pressure. This is air pressure. Okay. And it's the unit you get it back in is millibars. And I'm just going to see now. We'll probably see. Yeah, it's just under 1,000 millibars, which is probably about right because it's raining outside. I imagine the pressure is a bit low. Okay. Now you can't really affect this. I can't really breathe on this and change it. Sometimes if you press on it, you can make it change. If I just go back to that, if I just press on it a little bit, yeah, you can see I'm getting very minor changes just by squeezing it with my finger. Okay. But if you really want to do an exercise of air pressure, there's a really nice thing on our website which you can go and do, which I'm going to just go back to now. I'll just go back. So go back to this menu of learning resources and go to Astro Pi Guide. Okay, and then we're going to scroll down and find pressure. You can learn about all the different features on this resource. So pressure. Now, one of the things that's really nice to do, obviously, explain what pressure is and about the the Armstrong line and all this kind of stuff. And basically, what I recommend to do is to we've got the emulators embedded into this one a bit. You can run some code which just constantly measures the pressure. But what you can do is an exercise like this, where you essentially put a sense hat with one of those mobile phone backup batteries into a bottle. Okay, and you have a very similar program which maybe kind of works a similar way to that humidity one that we had before, which changes the brightness of the LEDs, and you essentially enclose the whole thing in a bottle and then exhale into the bottle to increase the pressure, and you see the LEDs going bright. And that's quite a fun exercise, and this resource here shows you how to do that. Now, I mean, the pressure will always be pretty much the same on the ISS, but what you can also do is there are variances in it where what happens is every now and then they do something called an O2 repressurization, which is where they release a whole new, basically a whole new bottle of O2 into the ecosystem of the ISS, and that causes the pressure to jump up a little bit, and you can detect that with that. But it's obviously it's not a good indication of crew activity. It's more an automated activity, and that resource, the flight data analysis resource, you can see that happening when you analyze those CSV files. Every now and then there's this sharp little, like, kind of the line goes along and jumps up and starts to go back down again, sort of thing. Okay. And what's the other one? The other one is temperature. Okay, so let's just go back and do temperature as well. And you can the shortest version of it is temp, or you can do temperature as well if you want to. So let's just run that. I'm going to see what it's coming up as in here. So it's about 22 in here at the moment. It doesn't feel like 22, does it? Now the reason it feels like it's about 18 in here at the moment. So what you're seeing there is actually the thermal leakage between the CPU and the temperature sensor. But usually you can affect this with your thumb, if you just or any kind of your finger. If I just the measurement's coming from the humidity sensor. So if I just put my finger over it now, you can see it's going up a little bit, up to 23. Yeah, it's not going up much because my fingers are cold. There you go. We might break 24 in a sec. There you go. So it's going up just by being in contact with my body. So you can get the kids to do this to verify that your temperature sensor is working properly. Okay. And again, the temperature won't really change very much. It might change a little bit if the crew are near you, but I don't think your best bet for trying to detect the crew is the humidity sensor. Okay. Okay. Right. So let's go into questions, and then we're going to be onto the we're going to get onto the movement sensor.
So there's a question, is the normal pressure in the ISS 1013 millibars?
Yes, that's basically it. It's basically sea level. That's what they keep it at. They try to keep it at. Yeah.
I think you've pretty much already answered the previous question, which was, is the sensor precise enough to detect normal changes of temperature on the ISS?
Yeah, it is. But obviously, you're also dealing with that slight thermal leak issue, which is when we made the first SenseHats, they went into the actual payload that went up to space, and then because we wanted everybody to have the same thing that was on the ISS, we had to keep that fault, if you know what I mean. We had to keep it in. So now all the SenseHats that you've got have got this same sort of little kind of, like minor bug with the temperature sensor.
So lots of people have been asking questions about the case with reference to temperature. So one question was, does the aluminium case transfer heat from the CPU to the temperature sensor?
The case doesn't. The case actually conducts heat away. So when you see one of these flight cases, you see it's got this massive pin grid on the bottom, and that's actually a heat sink. And in contact with the Raspberry Pi inside it, there's this big metal boss, which we'll do. Our focus has gone. There is this big kind of metal boss which is in contact with this part of the case. That bit there is all nice and smooth if you feel it on your Raspberry Pi. And there's a big metal boss which touches that and then actually conducts heat away through these pins. Okay, and the reason for that is that part of the qualification process for getting a payload into space is that you have to be able to never reach touch temperature, which is 45 degrees C. So this case must never reach 45 degrees Celsius, even if the CPU is under maximum load. So, and that's including it being up against a wall with no airflow. Okay, so if you think that's a really ridiculous heatsink for a Raspberry Pi, right? Because they don't generate that much heat. But what actually happens is in space there's no convection, so the actual normal processes of heat transference don't apply anymore. So you have to conduct everything away. No, air doesn't rise and fall like it does in a gravity environment. The air will just stay on the CPU and just bake and bake and bake. So that's what these pins are for on the bottom of the Astro Pi. They just take all the heat out and just conduct it away.
And finally, there was a question about if you are 3D printing yourself an Astro Pi case, does it make any difference if the 3D printing is done in black or in white or in a particular color?
Oh, it might do if you're in direct sunlight. Yeah, so if you've printed it in black like that, then yeah, it will probably absorb a bit more heat. But obviously the heat sink does nothing on the 3D printer because it's not conductive, and there's also no thermal boss on the bottom of it. We took that thing out of the CAD, so that there's because obviously it's plastic, it's not going to conduct any heat. So yeah, so you could get away without printing that heatsink part and just just run without it because it's not going to actually function as a heatsink. But we kept it in because all the kids like it because it's keeping the iconic shape of the Astro Pi sort of thing. Okay. All right. Okay, so let's move on. Right, now we're into like one of the most fun parts of all this. And what I'm going to do is I'm going to actually ask you to download a demo. If your Raspberry Pi is online, we can download a quick demo which will allow us to and this is basically what we're going to do. We're going to run this demo purely as a way of explaining the movement sensor to the kids. Okay, you don't have to do it, it's not 100% necessary, and I'm afraid I'm going to have to go back and use my my monitor again, because what actually happens is it's a 3D demo. And the 3D graphics is not drawn into like a window on the desktop. It's drawn straight into video memory, which my sort of VNC software can't capture. So I'm actually going to have to plug in a monitor and hold it up, I'm afraid, which is going to look horrible. But let's just quickly do this. Okay, so hopefully we see something on there. Okay, so now to download it, if we go back to the screencast, what you want to do is go git clone http://github.com/astro-pi/Apollo-Soyuz SOYUZ. Okay. Oops, I've already cloned it, so that's why it's going to give me this fatal thing. But you'll see it pull it down for you, and then you can go CD Apollo Soyuz, and then you've got this 3D demo. Okay, so now you see I've got Soyuz.py. Oh, you also need to install a 3D library. You need to go sudo pip 3 install py3d. If you run that, that'll install a little Python 3D library, which this demo depends on. Okay, and if you haven't got that, you'll get an error when you run it. Okay, so that's actually already installed. I'll just run that quickly. Yeah, it's already there. So now I'm going to run soyuz.py. Hopefully we will see something on this monitor behind me. Can you all see that? Let's just move that there. There you go. Can you all see that? It's a spaceship. Okay. Now what you do, you run this on your Raspberry Pis at school, and the kids will all see this. Okay. And then what you do is you just pick up the Raspberry Pi, and the Raspberry Pi is now sensing my movement. Okay. You can see it all moving, and I'm so you can do all these different ways of moving. So there's three principal flight axes which you need to tell them about. Okay. Pitch, roll, and yaw. Okay, and I'm sure most of you know what those are, but the best way to do it, pitch is this axis. So if you look at the Raspberry Pi, when you pitch it up like that, the SD card is like the booster rocket on this thing. So when I turn, that's the pitch axis going up and down like that. Now yaw is like steering a car. Okay, so that's if I do it that's yaw. Okay, and then roll is like barrel rolling a jet. You see that? That's doing a roll operation. See you can see the solar panels on this Soyuz module moving there. Okay, and then you press escape to get out of that. Okay, so that's a really nice little demo just to do that. I mean, that's just the only purpose of that. You don't need to get them to understand the code of it or anything. You just need to get them to understand what the sensor does. Okay, and that's a nice little demo that you can just download and run, and then they can see what it actually cognate in their minds what the actual idea of actual spatial orientation is. Okay, so let's just do a bit of code which plays with it. So let's I'm going to go back into the browser and just point you guys at the right part of the API for this. So what you want to do is, it's a bit further down, so python-hosted.org/sense-hat/API again, and then you can come down here, and then there's a whole section about the IMU, environmental sensors. We've done all that. IMU sensor. So IMU stands for inertial measurement unit. Okay, now every spacecraft since before Apollo has had these things on them. Okay, now the Apollo one is probably about this big. It's massive. Okay, and probably about 1 million times more accurate than this one. Now our IMU is a tiny little chip which is about 5 by 5 mil. Okay, so it's not amazingly accurate, but obviously we chose that chip because obviously the whole point of Raspberry Pi hardware is to make it all cheap and cost effective. Okay, so we couldn't have like a £1 million IMU like they have on satellites and spaceships these days, but it is the same thing, and you could technically fly like a small satellite or a CubeSat using that sensor. Okay, so let's go and do some programming here. Now, one of the things that you've got an orientation function which you can use, and it will give you it will actually give you it will give you the pitch, roll, and yaw angles. So let's go back to Python 3. I'm going to go File, New File, and then I'm going to have to type in my code again. Okay, so from SenseHat, import sense_hat. Oops, SenseHat. Sense equals SenseHat. Sorry about this, folks. Sense.low light equals true. You don't need to use this. That's just for the demo. And then we're going to go. I'm going to go sense. Actually, let's just do one. Just do it once first. Sense.print sense.orientation. Okay, let's just run that once, and you'll see what we get. We get these like orient as a saving. Right, let's run that. and then you've got this thing comes up. So you've got pitch 359, roll 1, yaw 176. Now you see that it gives it to you in huge amounts of decimal places, and that's because originally what you can actually ask for this in either Euler angles from 0 to 360, or you can ask for it in radians. Okay, so if I want to, I can go orientation underscore radians. If you're kind of like mathematically minded and rather work in radians, you can. So I just run that again. You see there we've got the radians of it. Okay. Now I'm going to prefer to work in normal angles, like compass angles. So I'm going to just keep sense to orientation. Now what we want to do is try and trim these down so that they look a little bit more sensible. Now this is actually what we call a dictionary object in Python. And if someone that hasn't actually ever used the dictionary option, basically it's named pairs of data. So this one's called pitch, and the data for it is after the colon. You've got 359, and then you've got a comma, which is the next piece of data in there. It's called roll, colon, and then the number, and the same for yaw. Okay. Now to access them, what we should do is do something like this. You can go O equals sense to orientation, and then you can go, well, let's do P for pitch equals O, and then you open brackets, and then you type in the key, which is pitch, and that will copy what's inside this data structure, that number, into P. Okay, and I can go print P, and that should just print the pitch. Okay, oops, run the code from here. There you go. All right, so let's do that, and then what you can do is, you want to clean it up a bit, you can go round, comma, say, and then after the comma it's the number of decimal places. So if I go round 2, that will round it to 2 decimal places. Okay, that's a little bit easier to look at and read. So why don't we do that? Let's do, I'll actually put the round as I'm grabbing it out of the array, out of the dictionary. And I'm going to go roll equals round. Oopsie. So round is a built-in function of Python. Roll, comma 2, and then yaw, and yaw. Oopsie, comma 2. Okay, and then I can do print P R Y. Okay, and then you'll see them, and that's a little bit easier to read like that. Okay, so now all I'm going to do is going to put all that in a while loop, while true, and then go in here, set to that. All right, so now that will just continually run those 5 lines. All right, run like that, and now you can see, now keep it on the screencast, but what I'm going to do is I'm going to start moving pitch up. You can see the middle numbers increasing. Okay, and move that back down, and then if I do roll, that's the middle, that's the, sorry, the one I was doing for, this is now the middle number, the first one was pitch. And then yaw is that end number. If I turn that around, you see that. So you can see it's actually very sensitive, and I'm kind of ragging the CPU by doing it like this without putting any delays in there, but that's fine to do that. And you can see how quickly the actual sensor changes value. Okay. Now what you can do with that, you can do all kinds of things with that. You can actually, if you really want to characterize what it looks like on the ISS, it drifts a lot on the ISS because the ISS is moving around the Earth and going through different sort of types of magnetic field. And the way it works is there's 3 sensors that are actually contributing to this measurement. Okay, you've got the accelerometer, a gyroscope, and a magnetometer. Okay, and they all combine the readings for them using something called a Kelman filter to produce these measurements. And what you find is on the ISS, the magnetic field is changing quite a lot, and also there's pretty much nothing on the accelerometer because they're in free fall, so you just get a bit of noise out of the accelerometer. And the only sensor that really sort of works very well in space is the is the gyroscope. Nothing really affects the gyroscope. So that's the one that works the best on the ISS. So go and have a look at those CSV files, and you'll see what these numbers are doing. And you can look at them as they go around the Earth, if you see what I mean. So as they change. What you can do, there's an extra function. If I go to the API reference, the first thing is this set IMU config. What you can do is, if you want to, you can actually turn off whether these things contribute to the orientation measurement. So you could do something like, if say you only want the gyroscope but you don't want the magnetometer or the accelerometer, you could go set IMU config false, true, false, like it is here. And that would then cause just the accelerometer to, sorry, just the gyro to be contributing to that function. Okay, and you can use any combination by using this set IMU config function. So let's just try that quickly. Just go back to here. So if I just configure it to start with, I'm going to go sense.set IMU config false, true, false. So this is now just looking at the gyro. Okay. And now you can see it's almost looks a little bit more stable because I'm not taking input from the magnetometer or the accelerometer. Okay. Now, have we got any questions about that before we move on?
We have a question whether the magnetic sensor is sensitive enough to be able to measure the Earth's magnetic field while the Pi is in space.
Yes, it is. It is definitely. You can get geomagnetic north out of it as well. If you there's an API function called get compass direction, which gives you the compass direction of geomagnetic north. Now, if you go and look at those CSV files that we looked at before, and then plot, say, the magnetometer readings, you see that they kind of like they circulate. They're kind of very period. There's a lot of periodicity in it, and you can, I think, I haven't ever tried it, but I reckon you could use that to count orbits, because you can just measure how long it takes to come around to sort of like a similar value. You see what I mean? But it kind of drifts a little bit, because every time the ISS goes around the Earth, it's not in a single orbital plane, because it's in low Earth orbit. It actually goes over a different part of the Earth every time it goes around, because the Earth's obviously rotating, sort of thing.
We also had some questions about, you were talking about CSV files and recording the data. Somebody's kindly put a link to one of the resources to do with AstroPi. Are there any particular ones that you would recommend that might be useful here? Yeah,
I mean, if you want to look at the kind of measurements that you're going to see on the ISS, then the flight data analysis one is really good. I'll quickly go open ones that are. So I'll go back to the AstroPi website. And the resources. So yeah, so the AstroPi guide and getting started with the sensor, I recommend everyone does those. Okay, those two are almost like definite essentials. And then you've got SenseHat data logger, if you want to create your own kind of data logger. Sensing Space is really good. Flappy Astronaut is quite fun. And then Magic 8 Ball is quite fun as well. Yeah.
So that's astro-pi.org/resources.
Yeah, that's it. That's the page that's got this like menu of resources on there. There's also a link to the resource for the AstroPi flight case as well. All right. So what I'm going to do is I'm going to move on to using the discrete sensors now, if there's no more questions. Yeah. Okay. Cool. So we're kind of running low on time now. We might not get enough time to do everything, but right. So basically, what you can do next is you can actually, if you want to just not look at the combination of all the sensors, you could just look at one of the discrete sensors, such as, so let's just go for the accelerometer. If I just do change that to, I'm going to change all these back to true, so they're all enabled. Don't want to disable any of them. Now I'm going to go A equals sense.accel, and then I'm going to change these to A. So I'm accessing A. What you get out of them is X, Y, and Z. And then I'm going to change these to X, Y, and Z as well. So it's nice to pull them out into separate values, and then you can go print X, Y, and Z. So this is just the accelerometer that I'm looking at now. Now the accelerometer, what it actually tells you is it's measuring the force of acceleration, which is being exerted on the sensor at any one point. Now, on Earth, that value should be, if it's resting, 1G straight down. Okay, so let's just run that bit of code. We should just get, oops. Oh, of course. What's that say? Key error X. Oh, it's Excel raw, sorry. That's what you have to do. Yeah, you use raw. If you go back to the API reference, you can. You've got Excel, which gets it in angles, and then Excel raw, which gets you the get accelerometer raw. Then you've got an alternative of it, which is Excel raw, like that. Okay, so then that will give you the X, Y, Z orientation. So there you go. So you see, like at the moment, the Z axis, which is the one that goes straight down through the middle of the Raspberry Pi, is showing about 1G. Okay. Now if I then go up to that, hold it up like that, then you can see that the 1G is moved over to the Y axis, so the X axis. And then if I move it like that, then you get minus 1G. And then if I hold it, say like that, that goes back to the Z axis then. And if I turn it upside down, I get minus 1G on the Z axis. And then, so what you can do, you can almost use this as a shake control. You know, for example, if I just do this, you can see I've got like some numbers. What I'll try and do is shake it and then hit Control C, so you see the numbers. So there you look, I've got it up to 2.6 Gs there, or minus 5.4 Gs at one point, just by doing a little shake with my hands. You know what I mean? Just like a little shake like that. So you could, one of the previous Astro Pi winners built this functionality into their MP3 player, so that you'd actually twist it like that to change tracks. So Tim Peake was actually up there sort of going, instead of actually pressing the buttons, he was going like next track, like that, which he thought was really funny. So you can use that almost as an element of input, but obviously with this particular mission, we've got quite a lot of restrictions on crew time. So any kind of crew input that you want to do isn't going to be possible. But I just wanted to show you that so that you know that the that sensors that's how you access like the raw values of each sensor. And the API has got some descriptions about how to do that for the accelerometer, the gyroscope. There's a raw gyroscope which gives it to you in radians per second, and also the magnetometer, which the compass raw, which gives it to you in nanoteslas. Okay. For those of you who are really scientifically minded. So I'm conscious that we've got about 15 minutes left. What I'd like to do is quickly go on to the mini joystick. Okay. So the joystick down here is basically got it's mapped to the cursor keys on your keyboard. So you've got up, down, left, right, and then the middle click. And the middle click is enter on your keyboard. Okay. Now the SenseApp does actually have some built-in functions to let you access the joystick. Okay. So one of the first things we can do is, let's just do a brand new file. Actually, let's just open one of my previous ones so I can copy it. Recent files. Let's do hello. Let's grab those first files out of it. Okay. So what I'm going to do, just this is a nice thing just to get the kids going with it. Just type in sense.wait for event like that, and that will, and then you can go print done afterwards. So what will happen is joy1. So just save that as joy1. So what will happen is that is one of the keyboard functions which will actually just basically make it pause on that line until something is pressed. Now, this isn't going to be, the joystick isn't actually going to be that useful to you for this round of Astro Pi, but hopefully in future rounds of Astro Pi we are going to get some crew time for the experiments. So But this is quite a nice exercise for you to do with the kids as well. The API reference is all down the bottom here. Joystick's the last part of it. Okay, so you can come down here and find out what it all is. So what I'm going to do, just going to run that, and what should happen is it just sits there and does nothing. Oops. Oh, cool. I've typed in the wrong thing. Maybe it's called wait for something else. Wait for event. Oh, I know why. Sorry, whoopsie. It's sense.stick. Wait for event. That's why. So make sure you do the stop. Make sure you do the dot stick. Okay. So now that should just wait for me. Now it's waiting for me to click the joystick. Okay. So I'm holding this up. I'm going to click it, and then done comes up. Okay. So that's a very simple thing to access the joystick. Now, one of the other ways of doing it, there's multiple ways of actually accessing it. So one of the things I like to do is do a loop where you just get the events and display them. So let's just quickly do that. I'm going to copy some code from the API reference here, which is going to help us. Here we go. This is what we want. Just grab that bit of code there. So we've got a while true. And then actually what I'm going to do, I'm not even going to do that. I'm just going to print sense.event. So what happens is this thing returns a list. Okay, and then what we're doing is going for event in that list, iterate over all the events that have happened and print the event. Okay. Now it's important to know that when you do this, there's actually multiple events that can occur every time you click a key. So whenever you press a key on a keyboard or whenever you press a key on the Sense app, there's two events that happen. There's a key down event and a key released event. Okay, for everything. So if I just press up, go back to the screencast. I just press and release up. You see that happens. So you've got the timestamp of the event, you've got the direction and the action. So you've got pressed and released straight away. Okay. So if I press and hold, you'll see that I get these held events, and then I release it and you get the release event like that. Okay. So you see I've got a whole bunch of I've got pressed initially, loads of held events, and then a released event. Okay, and it's important to understand that that's how the key system works, because you might just find, why am I getting two events when I press any direction? It's because it's giving you the press down action and the press release action, and the differentiation between that is a really important thing, especially if they're going to try and program a game or something. Because, like, for example, whilst you're firing, you want to keep firing whilst it's held, and then released you stop, sort of thing. Or so what we can do is there's a couple of other ways of accessing it as well. You can either do that, and like, for example, if you wanted to only do something when the up key is pressed, you could go if event dot, now is it's action, if event dot action equals pressed, then you can go if event dot direction equals, oh, actually need two equals this way for testing of equality, equals left, print left. Okay, so that's just basically me getting some code and only running this line here if the left key has been pressed. Okay, let's just run that. And what will happen now, I'm just going to shrink this window a little bit and move it up. I should only see something if I press left. So pressing all these other keys, there's left, 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 left. Okay. So that's basically, in a nutshell, how you can access the event system. There is another way to do it based on functions as well, which is where you can create something called a callback. So define a function called my left, open bracket, and then I'm just going to put that print left in there. And then instead of actually doing this looping way of doing it, you can just go sense.stick dot direction left equals my left. And then it basically every time the left key is pressed, it just runs whatever you've set this to. Okay, so if I just put while true time.sleep in there so that the program doesn't just exit, I can actually almost achieve the same thing as that. And sometimes you'll find that young people prefer to do it this way. So you've got the option. Okay, so then left. Okay. And you'll find that also now it's firing twice. If I press and release, so you get 2. So in here, you then probably, if you type in, I think you put event in there, you can then test the event type. You can then go if event dot action equals press colon, and then do print left. So that will only then give it to me when it's being pressed down. So let's just do that again. Yeah, so I only get 1 each time I click it now. All right. So, any questions about the joystick?
So, can people use the joystick in this experiment with the Astro Time?
I'm afraid there's nothing to stop you putting it into your program, but the crew on the station won't ever press it because we haven't got actual allocated crew time for the experiments. You might be lucky and they're interested and they just press it and wiggle it, but there's no actual kind of allocated crew time to actually go and press buttons on individual experiments, because there's going to be about 75 codes that we run on the space station from all the different European countries, and obviously having crew time to go through all of those and use them and stuff like that is actually quite a large amount of crew time, which unfortunately Tamar doesn't have. So we're just doing our best with what we've got at the moment.
Another question was about when you had the event logged from the joystick being pressed, there was a timestamp.
Yes.
What is the format for that timestamp?
That is the Unix time. So basically that timestamp, let me just, instead of doing that, I'll just change this code to print event. So we get that back, so we get that up. Run that again. Now if we just, right, so there you go. So you've got, basically that is the number of seconds since 1970. Okay. There are a couple of ways you can convert that. If you just Google how to convert Unix time into normal time, you can. There's a number of ways you can do it, and there's probably a bit of code that you can just copy and paste into your program. But the only reason you'd ever want to look at the timestamp is if something's happened in the order in which your events are occurring is somehow getting messed up. So, for example, sometimes the released event comes in before the pressed event, which shouldn't ever happen because the pressed event has to happen first before a released event can happen. But if you're ever seeing a situation where the released event is occurring before the pressed event, you can then look at the timestamp to see if it did occur earlier in time than the other one. So all you're ever going to be looking at that, and the reason it's a numeric figure is so you can just do less than and greater than on it. Okay. All right.
Thank you. Yeah.
All right. Any others?
We've had a couple of questions about sounds, whether it's possible to play sounds or to connect speakers.
Yeah, so this did happen in Tim's mission. What we did is we had a scientific sort of experiment competition for him, and then we had like an add-on competition where it was about actually making a crew care package for him. And what we did is we got the kids to program to make this thing into an MP3 player, and obviously it's got the the analog audio jack exposed. So technically, yes, they can plug in speakers, but we don't have the crew time for that for this mission. So hopefully, maybe for Alexander Gerst's mission, we'll be able to do it.
And is there any way to run 2 separate programs simultaneously? So, for example, the question says a program that controls the screen and another that performs the experiment.
You could do if you in your program Google the sub-process module. And what you could do is then have one program which runs, and then it runs 2 other programs simultaneously. So you'd actually have to have 3 programs that you submit, like the master one, and then the screen program and the experiment program, and what happens is the master program starts the experiment ones, and then if the master one closes, it kills the experiment ones. It kills the child ones. But there's a nice program called a nice module called subprocess that you can just import into your code, and then that will allow you to launch other programs as well. Okay. All right. So we're kind of running out of time, but what I want to do is just quickly go for building the AstroPi flight unit. Now, if you guys are going to do this, this is actually one of the things I've found is that if you do this sort of early on, the actual act of making something really gets the kids engaged in classroom activities. And once they've built this, if I just show it to you on alongside the actual payload, okay, you can see they are basically the same size. Okay, they're pretty much identical. Obviously, this one doesn't look as nice because it's made out of, you know, a PLA, and you can see that there's that kind of like stringy effect that you get with 3D printers. But I thoroughly encourage you to go off and build this, because and that's what this extra bag that you've got in your kit is for. This has got all the components and bits and pieces that you need to build up one of these. Okay, so now I'm going to just check to see if it's online, but I'm going to go back and go to YouTube. youtube.com/user/ESA/videos. Let's see if it's there. Yes, it's there. Excellent. Right, so if everyone goes to that URL, there's a video here called "How to Build a 3D Printed AstroPi Flight Case," which you can watch, and it will give you the exact step-by-step guide for basically building up one of these. Okay. And I really encourage you all to go off and do it. And what it gives you is an exact replica of the flight unit, and you can use it to test all these issues and to test to see if your code would work correctly on a flight unit in space. And that's the value in having one of these. So you can actually get the kids to really test what it's going to look like when the crew see it and when it's actually running on, you know, one of these. And the main issue you've got to watch out for is that most of the time we've been using the Raspberry Pi in this orientation, okay? But in the flight unit, it's in that orientation, okay? So one of the things you must make sure you do in your code, we're kind of overrunning a bit, but that's fine. I don't have anywhere to be, and I think it's raining. So one of the things you need to do is in your code, make sure you do sense.set rotation 270. Okay, that will then make the LED matrix rotate to the right angle so that that is the bottom. Otherwise, what you'll find is that the messages scroll upwards. Okay, and the other thing you can do is also the joystick doesn't have any knowledge of when it's been rotated, and all the kids that have done AstroPi in the past have always had to remap the keys so that they know. So for example, normally that's the orientation, so that's up. But if I turn it that way, up is still that way, which is now right. Okay. So what you can do, and this is if you go back to the screencast quickly, I've got a little example here which I made ages ago, which is called Flight. And one of the things you can do is just remap the buttons. Now this is something that you did, and I've ripped your code off. Sorry about that. So what you do here is, for example, what you do is just you go flight up equals direction up. So all you do is you just basically rotate the sense hat through 90 degrees, and then basically give yourself these variables called flight up, flight down, flight direction, right? And what you do is you always must make sure you go from sense hat import star instead of just sense hat import sense hat like we have been doing. Always do from sense hat import star, and then you get these things like direction left, direction right. And then you can see here when I'm doing my loop, I go if event direction equals flight up, then print up. Okay, so if I just run that now and hold the sense hat like that, okay, now I push up, I get the up events coming up. All right, so that's the way to sort of that's the way to sort of deal with the fact that the Raspberry Pi lives in a different orientation. So just remember, set orientation to 270, and then that remapping of those joystick events. All right. Now, before we go, are there any questions about that?
There are a couple of sort of general questions. One is about how schools and people using the Astro Pi will access the data, because they're wondering, is the ISS Raspberry Pi connected to the internet?
So when the ISS is actually not connected to the internet at all, it's on a very private network, and what happens is when the crew want to use the internet, they actually use a remote desktop to a PC on ground, so that only the video data is traversing the space to ground link, and then they can browse the internet at very slow sort of modem speed like that. But the Astro Pis are connected to the network up there, but they're only accessible on ground from one place in Switzerland at the moment. Okay, so what happens is you write your code, you program it to save a file, which is your data. Okay, your program runs, that file gets created, and then at some point after all the student codes are finished, the place in Switzerland will download all of the student codes, student experiment results, and then you'll get an email from us with your file that you created in space back from us. Okay, and then you can analyze it and see whether your experiment worked or not. Okay.
And do schools have to give back the Astro Pi kit?
I think that's up to ESA. I don't think you do have to give it back, actually. Although I'm not. If anyone's from ESA in the chat at the moment, please pop up now, because I actually don't know the answer to that. But yeah. Okay, so just a couple of quick housekeeping things as well. On the Astro Pi website, there is this area called Proxima. Okay, now the submission, when you've done your code, there will be a link around about here where I'm moving my mouse, which will say submit entry, and that's where you'll come. So it's astropi.org/Proxima, which is the name of Tamar Pesquet's mission. You'll click that, and then there'll be a form that you fill in, and then a couple of an upload button where you can upload a report about what you did, and then a zip file which contains all your code. Okay. And there's a forum link on there, so you click on the forum, you can go here, and you can actually, if you get stuck for any reason, come on here and go post a new topic, and then someone will possibly me will come and give you the answer. Okay, and then also there's an FAQ under Proxima as well, and if you've got any questions, this is actually quite a nice resource to look at. You can find pretty much the answers to all your questions are already on here. Okay. All right. Right. So, any questions before we sign off?
I think that this partly links to your previous question, but is there an internet connection while the program is running in space?
No, you cannot access the internet from your code. So, for example, if your code needs to pull a file from the internet, you won't be able to do that on the space station. Actually, any kind of access to the network is banned. Actually, if you look in the FAQs, if you attempt to access the network in your code, the JSL, it's probably one of the most highest security networks in the world, around the world. Then your code would just be disqualified from the competition. So do not do any networking in your code. Okay, just write out a local file into the directory. The current directory that you're in. Okay.
And finally, for people who might want to watch this webinar again afterwards, how will they be able to do that?
Okay, so the replay of this webinar will be on the same link as you're on now. Okay, so we just click that same link that you've got in the email from ESA, or bookmark the URL that you've got now. That will be the URL for the replay once we press the stop button.
And last question, I think, is there any possibility of the Raspberry Pi overheating if it's on for a long time working with the SenseHat?
Shouldn't be, no. Especially the one in space is actually a B+. So that's another consideration that you should. The one in space is a slightly older version of the Raspberry Pi than the ones you've got in your kit. So you've got the latest and greatest Raspberry Pi, which is the Pi 3, but the one in space is actually a B+, which is a bit slower, and also produces less heat. So yeah, I'd be very surprised if anyone managed to make their Raspberry Pi overheat. I can't think of, unless you put like a 12-volt supply in it, I don't think it's going to overheat. Yeah. Okay. Right, any questions? I'll just give them another minute or so for questions.
Are there any limitations people should consider for the B+?
Yeah, so the B+ is, I mean, if you do something that's really high performance on the Pi 3 and it runs at a fairly decent speed, what you might find is that then runs quite slowly when it comes to running on the B+ in space. And the only way you can really test that is to actually get a B+ and try it out. But if for example you put like timing like time.sleep 0.5 in your main loop or something like that, then it will pretty much run at the same speed. So just make sure that you've got some sleeps in your code to sort of like cushion it for when it goes on the B+ in space. All right, folks. Well, we've just overrun by about 8 minutes, but thanks very much for everything. We've got to be out of here in about 20 minutes, haven't we? So hopefully it hasn't snowed and we're not stranded here. So thanks very much for watching. And yeah, if you need to replay it, please feel free to. And by all means, please go and watch this video on the ESA YouTube channel, which will allow you to shows you exactly what to do to build the flight unit. Okay. All right. Thanks very much. Bye-bye.
Thanks very much, everybody.